This video is a short introduction to Taylor polynomials that we can use to approximate functions. So we're going to assume that we've got a function that we can differentiate n times. The first thing you want to get used to is some notation for that. So the nth derivative of a function, in other words, when you differentiate a function n times in a row, say, we're going to denote that by this f with parentheses n in the top. And so that means, again, take the nth derivative of the function. So to give you an example, f is this polynomial 3x squared plus 2x plus 1. The first derivative, maybe instead of using a prime, I'll use this kind of notation here. Just means take the first derivative, so that would be 6x plus 2. The second derivative, so again, instead of using, say, double prime, we'll just use this 2 in a parentheses up here in the exponent or the superscript, and that will just be 6. And then we see that any higher order derivative will just be 0, since you're taking the derivative of a constant for all n bigger than or equal to 3. So hopefully this notation makes sense. Now, what's the cool thing that we're going to do with it? So let's say we've got a function f whose nth derivative exists at some number x0, some real number x0. So I've kind of started to enumerate these. I'll call this bullet point 0, say, or step 0. So I can make a degree 0 polynomial. Remember, degree 0 polynomial is a constant. What I'll denote it by is p with a subscript 0 of x, such that p0 of x, p0 of x naught, again, the particular point that I care about, is equal to the value of my function at this point x naught. Maybe how you should think about this is these two graphs intersect each other when x is equal to x naught. So to give you a picture of that, it would be this over here. Say my red graph is my function, then I'm saying that I could think about there's this constant polynomial that's yellow that intersects my graph there at x0. So namely, let's just let p0 of x actually be the constant f of x0. Remember, that is a fixed real number. x0 was fixed ahead of time. Okay, so the next step, I can make a degree 1 polynomial. I'll denote it by p1 of x. Remember, degree 1 means the highest power of x you see is 1. Such that though, so the same thing as above, so p1 of x0 is f of x0. In other words, x0 comma p1 of x0 and comma f of x0, those are the same point on the graph. But then also the value of the derivatives of each of these functions match at the point x0. That's probably a better way to say that. So I think I've got a picture for you here. So I've got my red function there, and now I'm saying I've got a degree 1 polynomial, which is this line here that intersects my graph at that point x0. And also, though, the value of the derivative at each point matches. And so what is that? P1, what's a formula for it? It would be f of x0 plus f prime of x0 times x minus x0. So again, this is a degree 1 polynomial. This is trying to say x is the variable. And so, well, there's my highest power of x I see is just 1. Remember that this is a constant number, this is a constant number, and this is a constant number. So x is the variable. All right, so continuing, let's just do one more, say, and then we'll do the general case. So I can make a degree, there should be a 2 right here, polynomial, p2 of x, such that, well, p2 of x naught is the same thing as f of x0. p2 prime, the value of the derivative, is the same as the value of the derivative of my function, but then also the second derivatives have the same value at x0. So to give you a picture of that, I'm saying we should be able to find this quadratic, that parabola, where they intersect each other at x naught there, but then also like they have the same slope at that point, and then also remember the second derivative has to do with concavity, so they have the same concavity at that point as well, the exact same. So continue in this way. Oh, maybe by the way too, before I do that, what's a formula for what p2 of x? What's this, the degree 2 polynomial? How do you get it? Well, it looks pretty similar, and so what am I doing? Like this much here, that looks a lot like p1. In fact, that's exactly p1. And what we're going to do, and by the way, I'm using a prime here, so I guess I broke my convention. But now you see, when I take the second derivative, I'll get in back to the parentheses notation. So what is this? What's this coefficient here? This would be the second derivative evaluated at x naught divided by 2 times x minus x naught quantity squared. And again, why is this degree 2? Constant, constant. Well, this is degree 1, but then this piece at the end, when you think about FOILing that out, you would get an x squared there. That's why this is a degree 2 polynomial. All right, so continuing this way, you could probably guess, well, I'll just keep adding a bunch of terms at the end that look like this. And so I could find a degree n polynomial, say pn of x, such that, and what do I want to have happen? I want the value of the polynomial in f to be the same at x0. I want their derivatives to be the same at x0. And in fact, I want all their higher order derivatives to be the same at x0 as well. And so what does this say, by the way? This is trying to say that the kth derivative is equal to the kth derivative of the polynomial p. Pn is the same as the kth derivative of the function that you're starting with, for k equals 0 through n. And you're like, what's the 0th derivative? That's just saying the function itself. Think about when k is 0, think about this equation that is just talking about Pn and f. And so what's the formula for that look like? And so this is where it's a little bit subtle. You didn't see these from before with the factorials, but maybe you remember this. I actually need those in the formula to make this work out. So what do we do though? We just keep adding these pieces. The value of the nth derivative of x naught divided by n factorial times x minus x naught to the nth power. So I add up all those pieces. We will call Pn the nth degree Taylor polynomial of the function f centered at x0. So we either say f at x0 or we'll use the vocab or the phrase f centered at x0. Either one you like. People say each of them equally often, I think. Let me give you an example. So let's say we've got e to the x here, and let's say x0 is 0. So we'll say I want to find the Taylor polynomial centered at 0 for some degree. So what's something that we know about e to the x? Well, I know that its derivative for any number of times you take the derivative, it's always e to the x. So this is trying to say, right, the first derivative is e to the x, the second derivative is e to the x, the seventh derivative is e to the x, 1,000,000th derivative is e to the x. Don't care, it's always the same. So also too, when you plug in 0 to all of these then, that means that the value of any of the derivatives at 0 is going to be 1. It's cool. So I wrote that for you here. And then similarly, so let's actually write down, I just want to write down a few of the polynomials at different degrees. So the degree 0 Taylor polynomial would just be f of 0. In my case, that's just e to the 0, which is 1. So that a constant polynomial 1. The first degree Taylor polynomial for e to the x centered at 0 would be this form in general, and now you're going to plug in what you know. So this would be 1 plus x, right? Since this is 1 and this is x minus 0, that gives me x. Let's do another one. P2. So the second degree Taylor polynomial for e to the x at 0 would be, this is the general formula, you remember, from all the good yellow stuff we did above. And now let's plug in what we know. We said that this is 1, this is 1, this is 1. And so what do you get then? You get 1 plus x plus 1 over 2 factorial times x squared. Maybe, by the way, too, maybe you don't remember this. I just saw this too. 0 factorial is defined to be 1, and 1 factorial, of course, is 1. But maybe 0 factorial is the tricky part. It's defined to be 1. Anyway, so no one loses sleep over that. Whew. All right, let's do one more. P3. What is the third degree Taylor polynomial for e to the x centered at x0? Well, I know the form should be this, so I'm going to calculate each of these terms up to the third derivative and third degree here. And just when I plug in my numbers, same idea. 1, 1, 1, 1. So what should you have? You would have 1 plus x plus 1 half x squared plus 1 over 3 factorial x cubed. And so you could write this as 1/6 if you wanted to. That's fine as well. And so in general, if I keep doing this, what's the nth degree Taylor polynomial look like? Well, I think I see the pattern from this one. Since P3, I just did this little stuff up to degree 3 and over 3 factorial. For degree n, I probably just keep going, and I get this expression here. So the nth degree Taylor polynomial for e to the x centered at 0 is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. Continue that process up until you get to 1 over n factorial times x to the n. And what I'd like to do is to switch to Desmos very quickly, and just to show you what's going on. So I've graphed y equals e to the x for you. So here is the P0, right? The 0th degree Taylor polynomial. That's that blue. And here is P1. That's that green one there. So P2 is this purple one here, that parabola. I think I did P3 for you here. And maybe what I want you to notice is, if I think about points that are, say, near x naught is 0, right? So if I think about the graphs when you're around 0, it kind of looks like when I start here and work my way to the higher degree ones, maybe I could do that maybe one at a time. I got an idea. I got a little slider down here too. Desmos is pretty cool. So let's see. There, I'm graphed the degree 1. Now when I go to degree 2, it's the parabola. Degree 3, it's this cubic. What I want you to notice is that the graph of the polynomial starts to resemble more and more the graph of the exponential, e to the x. And so what we have then is these Taylor polynomials, like why are they important? Because they are polynomials, which are easy for humans to understand, and these things approximate a given function particularly well when you're close to a given point. So in other words, I see that if I'm near x naught is 0, these polynomials do a really good job of matching the graph. But if you look like to the left of -5, then like that's not a very good approximation anymore. So maybe we could look at, though, if you change the center and then try that. But anyway, the point is we take a higher and higher degree. In other words, as we take more and more terms in the Taylor polynomial, it looks like I start to get a better and better approximation to the function. And that is one of the important things for Taylor's theorem that's coming up.